this video, I'm going to be explaining power correction, which is the follow-up to my video on power factor. So if power factor causes there to be an unideal difference in the phase between a voltage and a current, then a power correction minimizes that phase difference. And it does that by adding power factor correction, which adjusts that phase difference back. So what I mean by this is my relationship from triangles from resistance to voltage to power. The only thing different between the three is you're multiplying by I to get from resistance to voltage and from voltage to power. But it's keeping track of, or consistent between all three. You have the resistance, which is real in all three. And you have the inductive or conductive resistance, which is the imaginary part, and that's also consistent in all three. And we have impedance, or the sum of both of those, in all three once again. So now this is taking the idea that if my original power factor looks something like this green line, where it's all the way down here, then I can add something to it that's gonna bring it back up to here, so there's less of a power factor. And if I'm looking at all these triangles, the resistance, the real power, is perfectly fine. That's like DC is consistent. But what's causing the power factor change is my inductance and conductance from my inductors and conductors. So now what I'm gonna do is I'm gonna find the value of an inductor or capacitor that brings this back up to make it a smaller power factor or a phase difference. And this is because inductors produce a positive J, where capacitors make a negative J. So if it was like this, and it was like down, say something like -60 degrees, I need to add an inductor to it, because that add more positive J and bring it back up. So now my new phase would be up to here. And you need to use the desired positive or negative correction that you need with the power factors positive or negative that you need. So kind of just explaining that idea again. If this was my original, which has constant R and some phase difference, then I'm adding, my R is going to be the same in all three, but now I'm adding some sort of correction that's a positive or negative J, depending on where it's at. And that combination of XLs is going to have a smaller new XL, which is going to make it a much smaller power factor. So some of the equations for this, that the I cosine of theta and I prime cosine of theta prime with your orange or your correction, those are going to have the same relationships. It's just a cosine relationship. That's always going to be constant simply because it's a cosine relationship. But that helps us determine any of our I magnitudes or angles if we need to be able to solve for these values. Okay. The next thing, that our new XL is going to be the sum of the original XL minus the correction XL. So see how we had this whole thing, then we added or subtracted this to it, and now it's this smaller gap. Okay. Then our new current magnitude is just using I equals V over R, but remember it's not R, it's XL or impedance or Z. So those are the three kind of differences of that XL. But it's just using that combination I equals V over R to solve for that magnitude of I, which would be this, or this in this case. And then my new theta is going to be the cosine inverse of R over XL. That makes sense. Or sorry, R over it should be this. Or in this case, it'd be XLT over I, but you know, I'm going to change that really quick. And that's again just using this trig idea that this is your new XLC, this is your I magnitude, this is your R, and this is your angle. And that's your new power factor angle or your new phase difference between the two after you've added an inductor capacitor with that positive or negative to make that phase difference smaller.